Do you have a question?
Yeah, on number 6, are these in order, or we can ignore the
A sequence is in order.
Alright.
So when you talk about sequence like this, it's an ordered set of elements. So yeah, the sequence matters. So we wrapped up Friday talking about C programs. And we were talking about how many C programs there are. And we agreed there were an infinite number of C programs, but we were arguing that there was a countably infinite number of C programs. Because in one case you could just take the ASCII code for each character, string them together from your first character as the least significant byte, and end up with a big long bit string that you treat as an integer. And that's the natural number to which that program maps. And it's a one-to-one correspondence between C programs and integers. And so it's accountably infinite. So cardinality of a set of C programs is aleph naught. And granted, most of those programs won't compile, but we can still count them. So I want to describe a function. So I want to pick a number r. It's a real number, and it's between 0 and 1, including 0, not including 1. That's not a critical detail, but it's a small interval of real numbers. And I want to define a function f of r. So for r equals 0.5, there's a function which I'll call f.5. For r is pi minus 3, there's a function which I'll call f.14159265. And this function maps from the integers to the integers. And here's how it does that. Fr of n is the nth digit of r. So for example, f0 of n is always 0. 0.00000, all the digits are 0. So for any n, it's going to return a 0. f.333, repeating forever, is going to be 3. The function f.25 well, the first digit of 0.25 is equal to 2. So this function will map 1 to 2. The second digit of 0.25 is 5, so this function maps 2 to 5. And the third, fourth, fifth, sixth, seventh digit of 0.25 is 0, so these are equal to 0. So it's a quirky little function, but its description is very simple. Fix some r, and this function takes an integer n and returns the nth digit of r. Is that clear? And can I write a C program to generate this function? Absolutely. Can I write a C program to generate f of 1/7? Absolutely. 1/7 is a repeating fraction. Can I make a C program to generate f of pi minus 3? Absolutely. We can calculate pi. We can calculate e. Now to calculate the millionth digit is going to take a while. But if I want to evaluate the value of let's say f pi minus 3. I can write a function that takes some integer n, calculates the nth digit of pi, that's what it returns. And it seems like for irrational numbers, transcendental numbers like pi and e, we can always write this function in C. But what is the cardinality of the set of functions f sub r? How many different functions do I have in that set? A what? An infinite amount. For any real number r, I have a function fr.
Which means cardinality will also be the cardinality of all real numbers.
And this has the cardinality of the real numbers, which is bigger than the cardinality of the integers. It's bigger than aleph naught. Since it's bigger, it means I cannot find a one-to-one correspondence between the elements in this set and the elements in this set. Anytime I try to find such a correspondence, there will be elements in this set that don't correspond to elements in this set. Which means if I take the particular correspondence of C programs to the actual function fr that they implement, there are some functions in here that don't correspond to any C program. Ergo, there are functions fr that I cannot write in C, even if I have no size limit on my C program. So there's a fundamental limitation of computers. Very simple mathematical function. We can compute it for simple and not so simple cases that we can think of, but somewhere there must be actually an infinite number of these functions that we cannot code in C.
And that would basically include like an irrational number plugged into, like if you tried to find an irrational, try to convert an irrational number to a binary number and use that binary number as the integer for the base of your C program.
Mm-hmm.
You can't do that because the integer is an integer. It can only be an integer. So if you got an irrational number, it has a decimal after it, and that cannot be converted into a valid.
Non-integer bases are interesting. That's a fun discussion to have sometime, because I don't know where that goes. I had a friend who called me up once, and he's like, "I just figured out there's actually no such thing as an integer," but he never did the follow-up call. But you can do things like that, like define a number system base square root 2 or base pi, and things that used to be irrational become rational, and vice versa. And I don't know what the actual functions are that you can't map to a C program, because any value of R that I can think of, I can write a C program to generate it, to generate the function fr. But this is an existence proof without actually creating an example. Kind of like what I mentioned Friday, any number you've never thought of that's a positive integer has to be bigger than 100. And we know that's true, but we can't actually come up with an example. Because as soon as we come up with an example, we've thought of that number. So it might be a little like that. So limit on computation, uncomputability. So C is not the ultimate language. And it's nothing to do with C, of course. It's any algorithm. All right, leaving that behind, let's talk about propositional logic. logic is simultaneously a good thing to know and a maddening thing to know. It's good to know because it helps you, well, think logically. It helps you draw conclusions that follow from other things. It's maddening because a lot of the world doesn't subscribe to logic. And the more you realize that, the more frustrating things can be. But even understanding the nature of fallacies, the nature of inappropriate or incorrect use of logic can be useful. Although with an entity that doesn't understand logic, you can't argue fallacies either. And that can be frustrating. So, what is a proposition? And we're going to come back to this definition again and again over the next several weeks. A proposition is a declarative statement that is either true or false. So here's some declarative statements. My name is Nick. It's declaring something and it's either true or false. 1 plus 1 equals 5. That is a proposition. It's a declarative statement. It's either true or false. Happens to be false. This is CSE 215. This is Baking 101. Things that are not declarative statements. Who are you? That's a question. Goodbye does not have a true or false value. So those are not propositions. So it seems pretty obvious, I think, but we're going to have to come back to this definition throughout the next few chapters and keep asking ourselves, are we talking about a declarative statement that's either true or false? Because you're going to be trying to solve problems, come up with proofs, and you're going to need to be working in the language of propositional logic, and you're going to need to make sure that the things you're dealing with actually are propositions. So those are propositions, these are not propositions.
So Russell's paradox is not proposition?
Say what?
Russell's paradox, is that not?
The way we stated it wasn't, if we said something like W is a self-consuming set, that's a proposition. But I don't think we got to that stage in Russell's paradox. We kind of threw up our arms before then. So a propositional variable is a symbol used to represent a proposition. So we might call this proposition N for name. This might be proposition S for sum. This might be proposition C for course. This might be proposition C2 for course. And we can use these like variables. And the truth value of a proposition is just true or false. Because we know if it's a proposition, it's either true or false, so we can say which is it. That's its truth value. And the study of this is called Propositional Calculus. So when your friends say, what are you doing? And you say, I'm doing Propositional Calculus. They'll be like, ooh.
How can you do calculus,
What does calculus mean?
the study of change?
Actually not. Calculus comes from the word for stone. Because stones were used for reckoning, computing, calculating a long time ago. So calculus was a term used for calculating or computating or things like that. It's not directly related to change, although the calculus that we study of real numbers is about rates of change and so on. But calculus is a more generic term, so we can like do calculations with propositions.
Doesn't it also include the basics of, okay, that was stupid, I was about to say, doesn't it include the basics of computing, which you just said?
Yeah.
I mean, I've heard of, it was called a lambda equation or something?
Yeah, like
Where
lambda
it's-
calculus.
Yes, that's it.
Yeah. Yeah, it's a widespread term, and sometimes I talk about the calculus of sibling rivalry, how to deal with that. So propositional calculus, so how old do you think this is?
Should be
5,000?
5,000?
Yeah, so this was Aristotle,
Yeah, so
300 BC,
so-
tried to formalize this. And one thing we can do with this is we can form new propositions from old ones. And that goes back in part to some of the work of George Boole in the 1800s. Boole isn't Boolean. I didn't want to erase those. But I did. So we have various Boolean operations we can perform on propositions. For example, if we have some proposition P, we can use negation. Yeah,
Is that like a proposition symbol?
that's a logic symbol. Here's a big version of it. It's a symbol that we call negation. So this is the negation of proposition P. So P, my name is Nick. Negation of P, my name is not Nick. Is this a declarative statement? Is it either true or false?
Yeah.
It's a proposition. It's derived from this proposition, which is also declarative and is either true or false. But it has the complementary truth value. If this is true, this is false, and vice versa. This is a symbol for what we call conjunction. Conjunction of P and Q. Or what you might think of as an and. So P, my name is Nick. Let's say Q, 1 plus 1 equals 5. So P and Q says my name is Nick. And 1 plus 1 equals 5. Declarative statement,
Yeah.
true or false? Yes. Happens happens to be false, but it's either true or false.
Oh, well, I see what you
English is wonderfully ambiguous. The V symbol, that's a disjunction or an or. And again, we get a new declarative statement that's either true or false by taking the disjunction of two propositions. My name is Nick, or 1 plus 1 equals 5, and that happens to be a true proposition. And we can just use the regular exclusive or symbol from 250 to say P is true, Q is false, or Q is true and P is false. The other way around. One is true, one is not. So it says my name is Nick and 1 plus 1 is not equal to 5, or my name is not Nick and 1 plus 1 does equal 5. And that's another declarative statement.
So the exclusive or, I know, you've seen chapter 1 with set theory. Do any of these other symbols work with set theory?
They do. They're actually exactly the same as a union, sorry, an intersection, a union, and a complement. And we can make truth tables of these operations. Because a proposition is either true or false, and so we can enumerate all the possibilities for the truth value of P, and the negation has a complementary value. Conjunction, same thing, each proposition is true or false, so we have 4 possibilities. And to say P is true and Q is true, we need both P and Q to be true. And disjunction looks like an or. And XORs look like XORs. Got the idea of propositions? So let me put this up here. Just to remind us. So we want to keep extending this, making more propositions out of existing propositions. And this leads us to conditional statements. So if P and Q are propositions, here's a third proposition. P arrow Q. So, yes. So this is the proposition, not quite a therefore. If P, then Q. From this we can get if P, therefore Q. So this is a proposition. So P Nick, Q, pigs can fly. Pigs can't fly, if you don't know about pigs. So P arrow Q is the proposition. If my name is Nick, then pigs can fly. It's a declarative statement, and it has a truth value of either true or false. So it's a proposition itself, and it's derived from these other propositions. And P is called the hypothesis, and Q is called the conclusion. And I've written if P then Q, but there's a dozen equivalents to that. If P comma Q, P is sufficient for Q. Q if P, Q unless not P. A necessary condition for P is Q. P only if Q. Q follows from P. A sufficient condition for Q is P. And there's others. It's partially the variety of English language. But we'll mostly stick with if P, then Q. And so we can try to make a truth table for this. So suppose P is true. And suppose Q is true. So let's say Q is, this is CSE 215. If my name is Nick, then this is CSE 215. That's true, and it's not implying a cause and effect. It's not saying if I changed my name, this would no longer be CSE 215. Or that someone else couldn't be standing here teaching CSE 215 while my name is still Nick. But if this is true and this is true, then this conditional statement is true. That can be a little fuzzy. We'll work on it some more. But if we go to a case where Q is 1 plus 1 equals 5, if my name is Nick, then 1 plus 1 equals 5. Is that if-then statement as a proposition in itself, is that true or false? If my name is Nick, then 1 plus 1 equals 5.
False.
That's got to be false, because my name is Nick, but 1 plus 1 is not equal to 5. So this it's a perfectly fine proposition, but its truth value is false. And we know it because this is true and this is false. So this is false. If my name is Betty, then 1 plus 1 equals 5. That's actually true. And that's not necessarily intuitive. But there's nothing that makes that statement false because my name is not Betty. It's just saying if my name is Betty, but it's not. This can be anything.
So if it's false, and then it's false,
The proposition is true. Yeah, and that one's troubling.
It would be easier to visualize if you put parentheses right after the if and right before the then.
Okay.
And then you drop a new statement where you've got if false, then 1 plus 1 equals 5.
Mm-hmm. Like this.
Because what we're actually doing is we're going, if this bit is true, then that means that this bit must be true. But in actuality, what we're testing is if his name is Betty, and that's false. So
Right.
that's pretty much the end of the whole thing. It
Yes.
doesn't matter what happens after that.
Right.
It's like you do in programming.
Mm-hmm. It takes getting used to. But it will probably make more sense the more we do conditional statements, but the more we encounter this statement also. What about false and true? Suppose Q says 1 plus 1 equals 2. If my name is Betty, then 1 plus 1 equals 2.
False.
We don't, we cannot say that.
So let me write this here. If my name is Betty, then 1 plus 1 equals 2. Why is it false?
Because the first
Because your name is Betty.
I'm not claiming my name is Betty.
It's just,
I'm claiming if my name is Betty, 1 plus 1 equals 2.
it should be free, I think.
Should be what?
Free, like, write two row files, carbon both of those.
Is 1 plus 1 equal to 2?
Yeah.
How can some statement that concludes 1 plus 1 equals 2 be false?
Because one of the conditions is false.
But we're not asking if these conditions are true. We're saying if this absurd condition is true, will this if this absurd hypothesis is true, will the conclusion be true? We don't believe that if actually I was lying and my name was Betty, that somehow 1 plus 1 would no longer be equal to 2. This is true regardless. If cows can fly, 1 plus 1 equals 2. If the sun blinks out tomorrow, then 1 plus 1 equals 2. This is actually true. So these conditional statements are only false in the case where the hypothesis is true, but the conclusion turns out to be false. Because the only thing the statement is saying is if the hypothesis is true, then the conclusion must be true. And the only way that you can say that's not the case is if this is true, but this is false. So this will be true in all cases except where hypothesis is true, conclusion is false. And I admit that's weird. But work with it. So given a conditional statement, we can form other propositions in the form of other conditional statements. So we can say Q, if Q then P, and that's called the converse. If 1 plus 1 equals 2, then my name is Betty. That's the converse of that statement. We have something called a contrapositive, which says not Q, if not Q, then not P. And finally, not P, then not Q, that's the inverse. So let me use a reasonable set of propositions for P and Q. P says it's 10:30, Q says we're in CSE 215. So if P then Q says if it's 10:30, then we're in CSE 215. That's a proposition. What does the converse of this proposition say in words?
If we're in CSE 215, then it's 10:30.
If we're in CSE 215, then it's 10:30. Is this proposition, if P then Q, is that proposition true?
Ignoring the ambiguity of Q, yes.
Yes. So if it's 10:30, then we're in CS 215. On a normal day, this is true. Is this proposition true?
Glance at the clock.
Nope. We're in CSE 215, but it's not 10:30, it's 10:40. So this proposition may be true, but this does not have to be true. But what about the contrapositive? So what does not Q say?
If we're in CC 215 and it's not 10:30?
If we are not in 215.
So not Q says we're not in CSE 215. So if we're not in CSE 215, then, and what does not P say?
It's not 10:30.
It's not 10:30. Is that proposition true or false?
Hopefully true.
That should be true. And in fact, this is equivalent to this. If not Q, then not P is equivalent to if P, then Q. And if you think about that, you can probably convince yourself it makes sense. This is saying if P is true, then Q must be true. This is saying if Q is not true, we've got to conclude P is not true, because if P were true, we know that Q would have to be true, but we're assuming Q is not true. So the contrapositive is equivalent to the original proposition. What about the inverse? If not P, then not Q. If it's not 10:30, then we're not in CSE 215.
Equivalent to the converse then?
It's in some ways equivalent. It's certainly got a false value. Is the truth value of this always equivalent to the truth value of the converse? What's the contrapositive of this statement? If Q, then P.
Not P.
So this and this are going to be logically equivalent because one's a contrapositive of the other. But mistakenly believing that this and this share the same truth value, that's a common fallacy. mean, sooner or later, it may as well be now. A lot of people use politicians and lying, but I use dogs and bacon. So what does this statement say?
If you're a dog, then you like bacon.
If you're a dog, then you love bacon. What does this say?
If you like bacon, you're a dog.
If you like bacon, you're a dog. Clearly not saying the same thing as this. What does this say?
If you are not a dog, you don't like bacon.
If you're not a dog, you don't like bacon. Again, that's not the same thing as if you're a dog, you do like bacon.
If you don't like bacon, you're not a dog.
If you don't like bacon, you're not a dog. That we can say. Because if you're a dog, you like bacon. That's what P implies Q means. So if you don't like bacon, you must not be a dog. And English is an imperfect language. That's an understatement. But when we say things in English, they may not mean what we would mean in propositional calculus, and we need to watch out for that. So this statement says, if you eat your dinner, then you can have dessert. What we really mean is, if you eat your dinner, you can have dessert, and if you don't eat your dinner, you cannot have dessert. But we say this in English, and we take it to mean it's a biconditional. In other words, if you can have dessert, then you must have eaten your dinner. Which is the contrapositive of this. So we'll sometimes use this, biconditional. And we mean both of those conditional statements. If you don't eat your meat,
Can you have
you
pudding?
can't have any pudding. Thank you. Nobody got that last term.
Really?
Yeah.
I was gonna suggest that when you said you eat dinner and have your dessert, but I just didn't, because it's like, okay, all right, we'll go on without that.
Yeah. So this statement is saying, if P, then Q. How can you have any pudding if you don't eat your meat? If you haven't seen The Wall, it's a quote from the movie The Wall. I saw it a couple of hundred times my senior year as an undergrad. It's why I'm warped today. How can you have any pudding if you don't eat your meat? How can you Q if you don't P, this is impossible. Or rather, this is impossible. This is a statement of the contrapositive. P implies Q. It's saying if not Q, then you can't have P. I think I switched my P's and Q's. It's saying that having pudding and not eating your meat, that's impossible.
Aren't the original statements not having your meat and not having your meat?
Yes, thank you. If you don't eat your meat, you can't have any pudding. And so if not P, then Q has got to be false, and so having Q true is impossible. That's something we call modus tollens. We'll have fancy Latin sounding names for various relationships that we can draw among propositions. And that's what the professor was citing in his little tirade. All right, we will look at truth tables of combinations of these conditional statements tomorrow. I won't be here tomorrow, Wednesday. We'll look at truth tables for these combinations. We'll look at equivalents and identities, and then we'll revisit existential and universal quantifiers for all and for some. And from there we'll do rules of inference, and then we'll start doing some proofs. And we'll be doing these things underneath all of our proofs. We won't always be formally saying this is modus tollens, this is conjunction, and so on, but it will be there. Okay, and we want to make sure when we're doing proofs, prove that the square root of 2 is irrational, prove that the square of an even number is even. We want to make sure that the steps we use to get from one statement to the next are following a logical processing. Okay, so this will get us where we can write correct proofs, which is going to be what we're doing for the remainder of this week. And then next week we're going to move into number theory, primes, divisibility, encryption, good stuff like that. That's all I got.